This is our video number 5 for magnetism, and in this video we're going to look at some principle of how AC motors or alternating current motors work, and additional some questions will be solved in this video. So the principle of an electric motor is based on the current carrying conductor, which produces magnetic field around it. A current carrying conductor is placed perpendicular to the magnetic field, so it is experiences force or magnetic field force. So every time you place the current inside of the wire with the current inside of the conductor, it will experience a magnetic field force acting on it. So in the picture on the right or on the top left side, you can see that there is a current carrying conductor that is placed between the two magnets and is connected to a battery. And so the battery would be the source of the direct current DC motor. But when the battery is turned on, there is a flow of the current in the conductor and the magnetic field from the north to the south. So you see there are two magnets, north and south. And by using the right hand rule, so let's say I have the current right here. I'm going to keep it green the way they have it. So I have a current floating in this direction. So I have to place my right hand rule where my current is aligned with the thumb, and the magnetic field lines there in red, magnetic field lines directed from north to south. So if you can place your hand where your finger is directed from north to south to show a magnetic field, and your current is aligned with your thumb, you will see that the force acting on the left side, so this is the left side of the wire, so the current acting on the left side of the wire, the force acting on the left side of the wire is going to be up, out of your palm. So this is going to show the magnetic field force. And then if you do the same for the right side, so the right one, then you will see that the force, if you use right hand rule, you will see that the force on the other side is acting down. So that will make the loop rotate in this direction. So if there was like an axis, the loop is going to be rotating in the clockwise direction. And when the current is parallel to the magnetic field lines, which is the back line, the one that I'm making thicker, when the current is parallel to the magnetic field lines, or this side, then there is no force acting on the parallel line with the current, or the parallel wire with the current. So this loop will rotate continuously and can be used to for mechanical advantage, for to do mechanical work, for rotating, let's say, a wheel. So this electrical energy can be turned into mechanical energy when you have a motor, the motor that is doing some mechanical work. And in both of these questions, well, in the right side question, you have the battery. So this is called DC motor, so because you have direct current constantly. But you can also have the source of the power, not the battery with the direct current, but you can also have AC, alternating current. And all this was observed about 200 years ago by Michael Faraday. This principle is used in wind turbines or water turbines when the water causes the wires to rotate. And so you can cause the current, what's interesting about this concept is you can cause the current in the wire by changing the flux inside of the loop. So the flux means right here, this area, how many, if we did the flux when we did electrical field, so how many magnetic field lines will pass through this area. So you have zero magnetic field passing through area in this picture, but you have more magnetic field lines passing through this picture because the loop rotated where your magnetic field is increasing, the flux is increasing, and the flux is equal to magnetic field times the area. And another formula for the flux could be mu N A and the current, and N is how many loops per length, and that indicates how many number of loops in the, so you see in each picture just one loop, but you can increase the current that will flow through, that will come out as a result, the current, or in that direction. So you will increase the current flow if you have more loops. You will have more potential difference generated. So there are two different ways to look at this. You can cause the current. So if you don't have the source, of electricity, then you can generate the source of electricity by forcing this loop to rotate. You can rotate the loop and the current is going to be created. Or if you connect the source to this loop, then the source will cause the current to flow. When the current flows, then the loop is going to be rotating. So again, two ways to create electricity. One is by attaching the source, and the other one by placing the wire in the magnetic field and changing the flux through the wire. So you can generate EMF. So between these 2 points, there's going to be potential difference, EMF, without having the source that causes the EMF. And that is equal to negative N, and then the change of the flux per time, over time. And this negative sign used in Faraday's law of electromagnetic induction simply by indicating that the induced EMF and the change in magnetic flux have opposite signs. In other words, it tells us about the direction of the induced field. There is an easy way to remember this direction. So the circulation of the induced field is equal to an EMF. So any current flowing as the result of the EMF produced in the magnetic by the magnetic field that opposes the flux changes that produces it. So the negative sign is like the opposition. So the current that will be created by the magnetic field when the flux is increasing or decreasing will oppose the changes. So if the flux is increasing, the current that will be created in the loop will oppose the increase of the flux, and vice versa. If the flux is disappearing from the loop, or there's less magnetic field lines passing through the loop, then the current will change its direction. And this, when you have a AC motor, it changes direction all the time. Then the current that will be, so when you lose magnetic field lines, the current will be created to support the magnetic field lines. It doesn't want to lose the magnetic field lines. And I will talk about this more when we have the example of the problem where we have the magnetic field causing the flux to, the loop is losing or changing the magnetic flux inside of the loop, and the current will be changing the direction, and we have to determine that current. So when we get to that point, when we have those type of questions, then I will point at it and explain in more details. Maybe let's look at this question and talk about the concept of the direction of the current when the magnetic field is changing. So the U-shaped wire of mass M is lowered into magnetic field B. So we have the magnetic field B that points out of the page, the plane of the page. So you see the dots represent the magnetic field line is coming out of the page. And if current I, 1, 2, and 3 is equal to each other and equal to 1 milliamp, And if the magnetic field is 0.5 Tesla and the wire is 0.1 kilogram, how much current must pass through the wire in order to cause the net force on the wire to be 0? So let's look at the direction of the current. So here I have the current is up. Here the current is down. And in this direction, the current is given in this direction. So it's just from the picture right there at the above. So if this is the direction of the current, then I'm going to use the right-hand rule. So my fingers have to point in the direction of the magnetic field lines. So that means you should have fingers toward you on your right hand. So your fingers toward you. Your thumb needs to be pointing in the direction of the current. So looks like your hand has to be parallel to the ground, and the force acting on the bottom wire is going to be up out of your palm. If I do the same for the left side, again, my fingers are pointing toward me, but the current is now, my thumb is pointing up. Then the force out of the page, the force out of my palm is going to be to the right. And if I do the same for the right side where the current is down, so now I have fingers pointing toward me, the current or the thumb is pointing down, and in this case I have the force acting to the left. So it looks like these two forces, the left and right, cancel each other because they're equal to each other. So the only force that we have to look is the force acting at the bottom part of the loop. Oh, and these were the lengths of the wire. So right here where it says 1 meter, so that's the lengths of the wire, not the currents. And the question is, how much current must pass through the wire in order to cause the net force acting on the wire to be 0? So the forces that acting on the wire is down, mg, and the magnetic field force. So in order for them to cancel, I have to set them equal to each other. So the magnetic field force must be equal to force of gravity. And the magnetic field force is equal to I LB sine theta, which is 90 degrees. The wire is perpendicular to the magnetic field, and equals to mg. So I'm looking for the current. mg is 1, mass is 0.1, and g is 10. And the length is 0.5. The length is 1, and magnetic field is 0.5. So I get 2 amps. In this next question, I have a rectangular loop of a wire with sides of 0.5 meters and 1 meter. So the sides are 0.5 meters and 1 meter that carries the current of 0.25 amps, and is placed in a uniform magnetic field of 0.5 Tesla. And what is the torque does it experience? You want to calculate the torque, which is the rotational force acting on the loop when it is in the magnetic field with the current. So to calculate the torque, you have the force times the distance, and the force acting on the wire is ILB and times the distance. So the L and B, and the sine theta, and L and D will give you the area. So the torque is equal to I, B, and instead of L I have the area, and then I have the sine theta. But then also it depends how many loops you have in placed in between two magnets. So if there's many loops around, then you will have more torque acting. So you multiply that by n, so the more loops you have, the more torque you're gonna have. So going back to our question, we have the torque is equal to B, the current, and then I have the area, and then sine theta, and times the amount of loops, and we have just one loop. And so the torque is equal to B is 0.5, the current is given 0.25, and the area is 0.5 times 1, which is 0.5, and the sine is again 90 degrees. And then we have the loop, just one loop. And the 90 degrees comes right here. So if the current is flowing in this direction, the magnetic field lines are going in that direction. So they're perpendicular. And the current that is going through the green part, they are parallel to the magnetic field line, so the force is not acting on that part. So if I plug in all these numbers and calculate my torque, I'm going to get the torque is equal to 1/16th, which is 0.0625 newtons times meters. So it's force times the distance for torque. I found this question on College Board for preparation for AP exam, and I use these questions usually for quizzes for you, and you should do these questions as well for your own preparation before the AP exam. So it says that the light bulb with the resistance R is connected by conducting wires to the top of the two log vertical metal rod that are a distance L apart. So you have the resistance of the conducting wires is R, and then there is the rod that it has a distance L. So here is the rod that is going to be sliding down, and the distance between the length of the rod is L. A horizontal metal rod of mass M, so the mass of the rod is given, mass M, is placed so that each end of it is in contact with a vertical rod. A uniform magnetic field of magnitude B is given, is directed into the page, you see little crosses right there, and perpendicular to all three rods. The horizontal rod is released from rest and it remains in contact with two vertical rods as it falls. The effect of friction and air resistance is negligible, so the air resistance and friction between the rods is negligible. Indicate the direction and of the induced current in the horizontal rod that is falling. So the force that is acting on the rod is the force of gravity, and this is why it is falling. When it is falling, it causes the flux through this area increase. When it causes the flux to increase, then it will produce the current. So there will be a current in this loop that will oppose the change of the flux. So the flux is the number, again, the formula for the flux is the number of magnetic field lines through the area, and then you have cosine of an angle between the magnetic field lines and the area. So the flux is going to be increasing, the number of magnetic field lines through that enclosed area is going to increase. So the current that has to be created has to oppose the magnetic field lines that are increasing. So if you have this loop right here, and the amount of the magnetic field lines is increasing with each second that the loop, that the rod is falling down, the current in it has to decrease the magnetic field lines that are passing through. So I need to create the current that opposes the magnetic field lines. So that means the magnetic field lines created by the current has to be coming out of the page on the top and into the page at the bottom. that will cancel that magnetic field going into by coming out of. So, and in this case, if I use my right hand rule, so I have to put my finger in the direction of the current, so this will be the current, and then I have to wrap my fingers around in the direction of the magnetic field. So in this case, if I wrap my fingers this way and there is the wire right here, then the current is in this direction if I choose it, then the magnetic field lines are going to be in that direction. So they're going into the page on this side and out of the page on this side. But I don't need this. I need the opposite. So because I need the opposite, then my current must be going in this direction. So the current must be going in that direction. So here is the current moving to the right in the loop. And when it's moving to the right, then I have to place my finger, my hand is going to go like this. This is my thumb. And then I have my fingers wrapped like this around the wire. And the current is in this direction, and the magnetic field lines are like this. So they are going into the page at the bottom, and they are coming out of the page on the top. And the ones that are coming out of the page cancel the ones that are going into the page, the magnetic field lines, that the foreign magnetic field lines. So the current is going to go to the right. In B part, they say in coherent paragraph length response, describe the forces acting on the rod and the rod's resulting motion when it is released from rest and after it is being fallen for a long time. Describe or include description of any changes in the current in the rod and the brightness of the bulb as the rod falls down. So the bulb is right here on the top, and in the diagrams usually the bulb looks like this. It's the circle with a cross inside. So if we use the right hand rule, and here is the current in this direction, and the magnetic field lines are going into the page. So if you place right hand rule or right hand so that your fingers go into the page and your thumb is pointing the direction of the arrow where the current is going, then you will see that the force acting on the rod is going to be upward. And the faster the rod is going to be falling down, so that's the magnetic field force. So the faster the rod is going to be falling down, the more force up is going to be acting on the rod. And it will reach the terminal velocity, or the point where the rod is going to stop accelerating downward, where the force, the magnetic field force, is canceling the force of gravity. So what you have to indicate is that as rod is falling down, it accelerates at first, and the current is increasing. As the current is increasing, so does the force that is opposing the fall, or opposing the gravitational force. And eventually the rod is gonna stop accelerating, and the two forces will be equal to each other. As the rod is accelerating, the brightness is going to go higher and higher because the current is increasing. And as it reaches the maximum velocity, the terminal velocity, when it's going to stop accelerating and it's going to be falling down at a constant speed, then your bulb is going to be at its maximum brightness. For C part, they say the apparatus is turned so that the three rods are horizontal now, as shown in the figure, the new one. And then it's the view above. An external force of magnitude F, so there is a force of magnitude F, so here is F, is acting on the rod and causes it to slide to the right with a constant speed. So we know that the velocity is going to be constant. And derive an expression for the velocity, in terms of the resistance that is given, the length of the rod, the force that is acting, and the magnetic field that is given, and the physical constant that is appropriate for this problem. So because the force that is acting, that is pulling the rod, is causing constant velocity, that means the force that is pulling in the opposite direction, the magnetic field force, is equal to the force that is applied. So the dark one is applied and the red one is the magnetic field force. So I can say that the force that is applied is actually equal to ILB, and the sign is 90 degrees, so I'm going to avoid writing that one. And then the current induced is equal to the EMF produced in that wire divided by the resistance, and then I have L and B. And in order to calculate the EMF, we have the formula. So here is the formula that I mentioned a little bit earlier. So if you want to calculate the EMF, it's the flux over the time, and the flux is equal to B times the area. So I have EMF, which is the change of the flux over the area, and then I have the resistance and LB. So the force is equal to, the flux is B times A, the flux is over the time, so this one is the time. So EMF is change of the flux over the time. So for EMF, I have flux over the time. So for flux, I have B times A, and then I have time and resistance, and then LB. And the area is equal to, so I have B and B, that gives me B squared. Then I have time and the resistance. And for the area, I'm going to write it is as L, the length of the rod, times the distance that it travels. So that's the distance. And then another L gives me another L squared. So now the distance and time, so I have the distance and over the time, that is the constant velocity at which the rod is moving. So I can rewrite this as B squared, L squared, and then instead of d over t, I can write the velocity that they mentioned, and then all of that divided by the resistance. So the force is equal to all this. And they ask you to calculate the velocity. So if I want to calculate the velocity is going to be equal to, I have the force times the resistance and divide by B squared and L squared. So you see a lot of questions on the AP exam, you do not have the formulas, you have to derive the formula. So never do memorize the formulas for any of the questions that we do. You want to be able to derive the formula and understand the concept behind every single question. I will stop this video at this point, and thank you for watching this video, and I will see you in the next video.